Hey everyone! Today we're going to pull back the curtain on one of the most important pieces of modern software, containers. We're going to totally demystify Docker and finally answer that big question, what is a container really?
All right, let's just dive right in. Look, if you've been anywhere near the tech world, you know what it's like. It feels like you're just drowning in a sea of buzzwords, right? And containers? Oh man, they are a big one.
You hear all these words flying around all the time, don't you? Kernel, namespaces, Cgroups, runc, containerd. It's just this alphabet soup of terms. And right now, it probably feels like a total blur of jargon. But I promise you, by the end of this, you're going to know exactly what each of these things is and how they all click together.
But what if? What if I told you that underneath all that complicated sounding stuff, it all boils down to one really simple, elegant idea? That's what we're going to do here. We're going to build a crystal clear mental model from the ground up so this whole thing finally just clicks. And to do that, we've got to start at the very bottom. I mean the absolute foundation of any Linux system. We're talking about the one piece that makes everything else even possible, the kernel.
So, what even is it? Well, the kernel is the absolute heart of the operating system. Think of it as the master program. It's the one that talks directly to the metal, the hardware, and it's in charge of managing all of the computer's resources. We're talking CPU, memory, disks, the whole shebang. You know, a really good way to picture the kernel is to think of it like the system's traffic cop. Seriously. Just imagine that cop standing in the middle of a busy intersection. Every single request from every single app you're running has to go through the kernel first. Its job is to direct all that traffic, making sure nothing crashes and everything runs smoothly. It's the ultimate gatekeeper.
Okay, and this right here, this brings us to the most important point about containers. If you get this one thing, everything else makes sense. Ready? Containers do not have their own kernel. They all share the same kernel, the one on the host machine. And that single fact right there is why they are so unbelievably fast and lightweight, especially when you compare them to something like a virtual machine.
So that begs the question, right? If all these containers are just sharing one kernel, how in the world does the kernel pull off this magic trick? How does it create a totally private, isolated little world for each and every one? Well, let's find out.
But hang on. First things first, we have to clear up a super common misunderstanding. A container is not just a small virtual machine. It's not. A VM, that's a whole separate heavyweight operating system running on top of your own with its very own kernel. A container? Well, a container is something way, way simpler and honestly more elegant. So, what is it then? At its very core, a container is just a single process. That's it. A single process that's running in an isolated environment. And here's the key. That environment is specifically designed to trick the process into believing it's all alone on the machine. It's a complete illusion.
And where does that amazing illusion come from? Well, that belief, that feeling of being all alone, is carefully crafted by, you guessed it, the Linux kernel. And to pull off this really impressive trick, the kernel uses two secret ingredients.
Ingredient number one is something called namespaces. This is the kernel feature that actually creates that illusion of isolation. The best way to think of them is like invisible walls. So a PID namespace gives a container its own list of processes, making it think it's process ID number one, the first and only process. A net namespace gives it a private network. MNT gives it its own file system. You get the idea. Namespaces basically just hide the rest of the system from that one process.
But, just hiding things isn't really enough, is it? Just because a process can't see the other processes doesn't stop it from being greedy and trying to steal all the system's resources. So while namespaces are great for creating the illusion of isolation, we also need a way to actually enforce some rules, some resource limits.
And that's where our second ingredient comes in, Cgroups, which stands for control groups. You can think of these as the rules of the house. Cgroups let the kernel lay down the law and say, hey you can only use this much CPU and this much memory and that's it. They're absolutely crucial because they're what stops one misbehaving container from hogging everything and bringing down the whole server.
Okay, so let's recap. We've got namespaces for the isolation and we've got Cgroups for the limits. And remember, both of these are just features built right into the Linux kernel. So now, let's start putting these pieces together. Let's connect these low-level kernel ideas to the tools you actually use every day, like Docker. See, when you type a Docker command, you're not actually talking directly to the kernel. There's a really nice, clean separation of jobs here. You've got this thing called containerd, and it acts like the manager. It's the boss. It handles things like pulling down images and managing the whole life of the container. And then, reporting to the manager, you have runc.
And runc is the real worker bee. It's the low-level tool that gets its orders from container D and then does the dirty work. It's the one that talks directly to the kernel to set up all those namespaces and configure the Cgroups we talked about. This is the piece of software that literally turns a plain old process into a container.
All right, time to put it all together. Let's trace the full journey, from the moment you hit enter on your keyboard to the second a container is alive and running.
Okay, so you type docker run. What happens next? First, your command line talks to the Docker daemon, which is called docker deed. Then, docker deed hands off the request to our manager, container D. Third, container D tells the worker, runc, to get to work. Step 4, runc does its thing. It uses those powerful kernel features, namespaces, and groups to build that isolated little world. And finally, your process kicks off, running happily inside its brand new container. See? It's not magic at all, just a few simple layers.
So if there's one thing you walk away with today, let it be this. A container is not a tiny computer. It's just a regular Linux process that's been given 2 superpowers by the kernel. Isolation thanks to namespaces and limits thanks to groups. That's it. That is the core idea. Once you really, truly get that, the whole world of containers suddenly snaps into focus. And it makes you wonder, doesn't it? What else out there in tech is really just a clever illusion built on a few simple but incredibly powerful ideas?